Okay, so we're working on a couple more examples from section 4.7, the optimization section. And so in this example, we have a boat out in the lake or maybe out in the beach somewhere. 4 miles, I guess 4 miles. We'll take it from shore, and that's a straight line distance, right? So that's a 90-degree angle. And then the straight line shore goes for 6 miles down to the lighthouse. Okay, now I can row at 2 miles an hour. I walk at 3 miles an hour. Uh, I guess it's hard to row that big boat. Okay, so the question is, where along the shore should we aim the boat so that we minimize the travel time from the boat to the lighthouse? So is this sounding familiar? You'll also remember that we're using the formula distance equals rate times time, or to put it directly, distance over rate is equal to time. Good. All right. So it's good to try out the extreme situations first. So trial 1 is we'll just go straight into the beach. And so let's make this x right here the distance from the point on the shore to wherever we land the boat. And so we can call it x equals 0 then, right? And so then we're moving 4 miles at a rate of 2 miles an hour. So that's 4 divided by 2 will give us our time, plus, what is that, 6 over 3. And so that's going to give us 2 plus 2. So it looks like 4 hours to go straight to the shore, and then from that point on the shore walk to the lighthouse. What's the second trial? Well, that's going directly to the lighthouse, so we're not going to walk. We'll row the entire distance. And so in that case, x is equal to 6, right? And then the distance will be the square root of 4 squared plus 6 squared. And then the rate will be 2, right? And so that'll be our total time. And so that looks like about square root of, that's 36. 36 and 16, 52. So that's going to be the square root of 52 over 2. All right. And so that turns out to be, oh gosh, the square root of 13, which is approximately 3.6 hours. Okay, so now our last version of this is to, just go x units in, right? And then travel the rest. So if that's x, then this will be 6 minus x, and that makes my time in terms of x easier to compute, right? So given x, then this is going to be the square root of, it looks like 16 plus x squared, right? Divided by 2, plus, and then 6 minus x divided by 3. Good. So this is very much like our last problem like this. These are very similar. They all have the same flavor. And so we've already checked the endpoints now. So now we just have to check the critical point. And so that's what we're going to do now. Check the critical point. So that's going to be 1/2 times 16 plus x squared to the minus 1/2 times 2x. And that's all divided by 2. Right, and that's going to be minus 1/3. And so we can simplify this a lot. So that's going to be, let's see, x over 2 square roots of 16 plus x squared, right? That'll be equal to 1/3. If I set that equal to 0, cross multiply. Square both sides, but you have to be careful when you square both sides that you might introduce spurious solutions. Good. All right, so we're just about there. So let's see, 9x squared minus 4x squared will be 5x squared. So that's 64. And so therefore x will be 8 over the square root of 5. Good. And then if we double check that number on a table, right, with x and our t of x, we went 0 and then 8 over square root of 5 and then 6, right? 0 was 4, and then if I plug in 8 over the square root of 5, I get approximately 3.5, and you can double check that. And with 6, we computed that to be about 3.6. Good. And so therefore, to minimize our travel time, we will take we'll take x to be 8 over the square root of 5. Good. And then it'll take about 3.5 hours. Excellent. All right, so we've got about 4 more minutes, so let's try another one. I'm going to pause while I write it down. Okay, so let's read this one. Find the dimensions of the right circular cylinder of greatest volume that can be inscribed in a right circular cone shown below with radius b and height a. So the right circular cone that we're thinking about looks like this. Okay, so we said that the radius was b, so b is the radius here, and then the height, actually the height should be a, not h, sorry about that. Oops, a. Good. And now what we're talking about with this right circular cylinder is that it's parked right in the middle, right? Good. And so this is going to be length r, and this is going to be height h. Good. And so then the volume of the cylinder is going to be pi r squared h, and that's what we want to maximize. But of course, that has 2 variables in it, so we need another formula or a way of writing one expression in terms of the other. Well, let's focus on this. I see a triangle in here. Do you guys see it? And the triangle is looking like this, right, where this is b and this is a and this is r and this is h, right? So is there a relationship between those variables? Well, there's different ways we could write it, but a similar triangle says b is to r as a is to what? A is to a minus h. Oops. Good. So b times a minus h is equal to a times r. Which direction should we go? We'll write h in terms of r, maybe. So let's see. So that's ab minus bh equals ar. I guess I could have just, well, that's okay. So therefore, let's see, AB minus AR is equal to BH. And so H is equal to, divide everything by B. Good. And, or let me rewrite that as A minus A over B times R. Right? And so now we see what we need to do. Now that I've got H written in terms of R, by the way, is there any restriction on H? Or is there, I guess we're going to write everything in terms of R. So is there a restriction on R? I guess we could go ahead and write the volume in terms of R is going to be pi r squared times A minus A over B times R. And then R is going to be between 0 and B, right? Good. And you'll notice that the volume at 0 is 0, and the volume at B is 0. Yes. Good. And so we're kind of back to the same kind of problem we had before, right? And so it's probably easier to go ahead and multiply this through before we differentiate. So we could say the volume is a pi r squared minus a pi over b times r cubed, right? So then dv over dr is just 2a pi r minus 3a pi over b r squared. Good. And now we're going to solve for where that's equal to 0. So go ahead and factor everything out that's common. It looks like there's an a that's common, a pi that's common, an r that's common. So that's just going to be leave me with 2 minus the a and the pi are gone, so that's going to be 3 over b times r. Good, so therefore r is equal to 0, and we're not going to use that one. Or r is equal to 2/3 b. And I think we would use this one, right? Because we already said that the volume at the endpoints was equal to 0. And so whatever our critical point was in the middle, that's got to be the max, right? It doesn't really matter what the maximum volume is. However, we did want the what am I trying to say? The dimensions. So we're going to take the cylinder with radius 2/3 b, and then the height will be a over 3, I believe. You can double check that. Very good. So that's a bunch of examples from section 4.7. These are kind of fun. Once you get the hang of it, you'll see kind of the similar themes. Did you notice what the similar theme is that we've been talking about? This is kind of a typical issue, right? That you get some kind of function in more than one variable that you want to maximize or minimize, but then you have a side constraint that you can substitute in to make that function a function of one variable. And as soon as you do that, you either have a function of one variable over a closed interval, or we may have to try something else with that first derivative like we did in an earlier problem. Okay, I'll let you try a few of these out, and I think I might post these on our website so that you have these examples in hard copy. All right, I'll see you later.